I'm going to talk about two factors, which were introduced by Robin some lectures ago. So let me remind that the definition was as follows, that if we have a von Neumann algebra inside B of H, then and we assume it is a factor, which just means that the center of the algebra is trivial, then a 2-1 factor means two conditions. That first, that one is a finite projection, and hence every other projection is finite, and there are no non-zero abelian projections. But in practice, this is not the conditions one usually tries to check directly. So there is a nice characterization, going back to von Neumann, which says the following. So assume that we have an infinite dimensional factor. Assume inside B of H is an infinite dimensional factor. Then the following conditions are equivalent. On the one hand, we can say that M is a 2-1 factor. Another way is to say that there exists a ratio state. So where ratio just means the visual ratio property that tau of xy is equal to tau yx.
Do you need normal?
No, you don't need normal. But moreover, as soon as you have this, then you can say more. Moreover, if 1 and 2 are satisfied, then this tau is actually unique. It is normal. And recall that normal means some continuity property, but a short way of saying this is to say that if you restrict tau to the unit ball of the von Neumann algebra, then it is continuous in any of those operator topologies. I mean, in addition to the normal one. And in addition, tau is faithful. And recall that faithfulness means that if you take a non-zero element, then tau of x or x will be strictly positive for every non-zero element. Okay? So, in practice, then, if you should come up with a von Neumann algebra with a trace, and then basically from this it will follow that a given von Neumann algebra is a factor if it happens to be a factor. Yeah, let me say something about not the proof. So the difficult part is to show from 1 to 2 that if you start with a 2-1 factor, then such a trace it exists and has all these properties. The easier part is from 2 to 1, and maybe for tutorial I will leave a part of this implication as an exercise. Say if you already know that say tau is faithful, so if tau is faithful, it's a faithful trace. then every projection is finite. Okay, so if you try to solve this exercise, then you realize how good it is to have faithful traces around. And then the question is, where do they come from? And it turns out that they simply come from traces on sister algebra. So as soon as you have a trace on a sister algebra, you can construct a von Neumann algebra with a faithful trace. So let me discuss this here. So let us assume that we have a sister algebra with a trivial state. And 2 is a trivial state. So then, as we know, we can construct the GNS representation. So let's consider this GNS triple H pi psi. We know that this means that we have a representation from A into B of H, and we have a unit vector such that by considering the state defined by this unit vector, we recover our trace store. And my claim is that if we take the von Neumann algebra generated by A, where we will be exactly in the situation when we have a faithful trace. So let us just simplify a bit the notation. So let's forget about the kernel of A. So let's just assume that A is already inside B of H. Replace A by pi of A. So in other words, the situation we have is the following. So we assume that A is a concrete sister algebra inside B of H. We have a cyclic vector. So in other words, H psi is dense in H. And we assume that this vector defines a trace. So A is H psi psi. And we assume that this is a tracial vector, so tau is a trace. Okay. So then the claim is that if we consider the von Neumann algebra theorem, so we consider the von Neumann algebra generated by the sister algebra. And we extend our trace in the obvious way to the entire von Neumann algebra. So we define for x. I will use the same notation because it's the same formula. Then the claim is that the following is true. So we have this nice operator which appeared in yesterday in Robin's talks, but here it's much easier to define. So the operator J from xi to xi, which maps xi into x star psi. So extends to an anti-unitary, in other words, anti-linear isometric unitary involution. So involution just means that the square of this is this much. Well, the second property is that this involution does like this, that if we take the conjugate our von Neumann algebra M by this involution, we get exactly the commutant of this von Neumann algebra. theorem is that our trace stored is actually faithful. Faithful on M. Or in the terminology which Robin used yesterday, this is the same as saying psi is a separating vector for the von Neumann algebra. Okay. So this is a particular case of this modular theory which Robin talked about yesterday, but this is kind of a baby version of it. It existed way before modular theory and was an inspiration for the development of modular theory in the general case. And in this case, it's going to be proved very, very quickly. So let's just do it. Okay, so concerning one, there is really not that much to prove. We just have to check that this operator J is indeed well defined and isometric, and then it will stand by continuity to anti-unitary, and its square will be 1 simply because taking the adjoint twice will be the element X back. The only thing we want to check is whether this is indeed isometric. So let's try to do it. So we take the image. Want to compute the norm. So by definition, it's star psi. Right. So by definition, this is tau of x star. But here now we use that tau as a trace, which greatly simplifies things. So x star x, and so therefore it will be exactly the same as x star squared. Everything works nicely. Okay, now we'll prove part 2, which is the main part. Let's see what these operators J, X, J actually do in our space. So let's try to compute it. So we take an element J, X, J, and let's see how it acts on element of, say, Y psi. So we use the definition, so we apply the first J, this is J, X, Y star, psi, then we apply the second J, so we have to take a joint, so we get Y, X star psi. So we see that what this operator does, if we sort of ignore this psi, then this operator is the operator of multiplication on the right, while our original operators are operators of multiplication of the left. So this becomes kind of even kind of more visible if we use the notation which Robin used. So let's call eta of x psi, right? Then in this notation, we have that if we apply operator jxj to eta of y, then this is eta of y x star. But if we apply x to eta of y, then it's just eta x y. Right, so our original operators act on multiplication on the left. Our new operators act on multiplication on the right. Which obviously these things commute. So we get that dmj is contained in M prime. So we're good on track to prove what we want, but this is still not what we wanted. We want exact equality rather than this inclusion. And for this, we can try to repeat the same, but now replacing the commutant with M itself. But for this, we have to be sure that our J does the same thing. So let's try to do it. Next, claim that if X is an element of the commutant, mod of M, the commutant, then J does exactly the same things as before, so that the J x psi is actually x star psi. Okay. Well, let's prove it. So to prove that two vectors are equal, we can just take scalar products with a dense set of vectors and see whether scalar products will be the same. So let's try to do it. So let's take y in right? So we have to compute this product, but X is an element of M prime. But we already know that J is anti-unitary involution. So when we apply J's, then the scalar product basically remains the same, but we have to remember that it's anti-unitary, so it changes up to complex conjugation. So in other words, this is the same as this product if we apply. So I apply J to both sides. And so this is y star psi, x star psi. Or I can move everything to one side and say this is x, y star psi psi. Did I miss something? Okay. Well, on the other hand, we have that. The x and y compute, but I'm still confused about it.
If you want to check the identity on the right,
Hmm? Sorry?
you want to check the line?
Yeah. So yeah. That's it. Thank you. Thank you. Because otherwise there is something. Everything is correct, but it's not going to work like this. Now, if we take x star psi and y psi, then we get that this is the same, and y star x star psi, and these are the same things because x and y have. So therefore, we get what we wanted. That J looks exactly the same as before, and so for exactly the same reason we had this property, we get that the property that J m prime J is contained in the double commutant of M, which is M. Right. And this means that we got what we want. That M prime is exactly J M J. Okay? So this proves part 2. Let's do part 3. So now let's just check first that xi is a cyclic vector for M prime. So what we have is that M prime psi is, let's say, as Jm J psi, which is the same as M psi. So this is dense in H. Therefore, if we have that of x is equal to 0, so what it means, this means that x psi is equal to 0. But then if we apply M prime on the left, as M prime 0 is M prime x psi, is x M prime psi, so we can conclude that x is actually equal to 0. This is what we want. Okay. So starting from any ratio state, we can actually construct a von Neumann algebra with a faithful ratio state, and with this additional nice property that the relation between that von Neumann algebra and the formutant is given by conjugation by J. So let's consider some examples. Yeah, I guess not supposed to write much more than this slide.
example to see those three frames, how it's not threshold.
This property?
Yeah, if you don't assume that,
Yeah,
of course, how it's threshold.
Yeah, this is I mean, typically, if you have so if you start with any state, right, and you construct GNS representation, then the vector will be cyclic, but it's not going to be cyclic for the commutant. In the simplest case, for any pure state, it's not going to happen, right? So then the commutant is extremely small. But a more general version of the same result is to say that if you start with a k-mesh state, then it's still fine. Okay, so let's consider some examples. So we'll start with examples which was introduced by Robin yesterday. So let's consider the sister algebra, which is infinite tensor product of just 2 by 2 matrices. Another way of thinking of it is that we take the increasing sequence of matrices of the size 2 to the power n, and take the completion of it where the embedding of each matrix algebra into the next one is given by doubling the matrix, so doing things like this. So we get this Stew closure in the norm topology. So we have this sister algebra, and on this sister algebra there is an ice trace, only one. So we take the simply tensor product of normalized traces on 2 by 2 matrices. Or, in other words, in this picture, this just means that we take the usual operator trace by normalize so that we have a trace on each of them. We get such trace, and then the von Neumann algebra which we're going to get. This is what is called the hyperfinite one factor. It can be checked that these kinds of constructions, so infinite tensor product of factors is always a factor. So one can check that this is indeed a factor. So from like this result, we only know that this is a nice von Neumann algebra with a faithful ratio state. But in addition, one can check that it's indeed a factor, and as a result, we conclude that it's one factor. Okay. So. But let's consider some other examples. So here the trace comes from just operator trace on matrices, but there are traces of very different nature. At least they look quite different. So let's consider some examples. So we'll start with a discrete group. And consider its regular representation, left regular representation. So this means that, so if we take so this L2 spaces, it's, the orthonormal basis is given by delta functions at gamma. And what this representation does is simply shifts these elements of this basis according to the action on the left. And so the von Neumann algebra of gamma is defined as the, so let's say that this is a span of this lambda of gamma, double fold. So this is some von Neumann algebra, but it actually has a very nice trace. Namely, we take a vector defined define 2 of x by this particular vector corresponding to the delta function at the unit element. So what does it do? you have a finite combination of these operators, so we're dealing just with finite number of operators. And what it picks up, because every lambda g, it moves e to some other element of the basis. And if g is different from e, it will be a different element. And so it will not contribute to the values. So what it does is simply picks up the coefficient at identity. And from this, one can easily see that it's actually at ratio state. So you just have to check that tau of lambda g lambda h is equal to tau of lambda h g. So it's lambda h lambda g. Or in other words, you have to check that tau of lambda g h is the same as tau of lambda h g. And this is certainly the case because we're supposed to pick up on the coefficient of 1, so this is non-zero only if g and h are inverse to each other. The same is true here. Right? So therefore, we're exactly in the situations which we considered. So we have a von Neumann algebra. We have a cyclic vector because when we act by all these elements lambda g, we get a dense subspace of our space. And this cyclic vector defines your ratio state. So the conclusion is that this is actually a faithful trace on the von Neumann algebra. So this is a von Neumann algebra, and then if we're interested when we get a 2-1 factor, the only thing we have, which is we have to check, is whether this is indeed a factor or when is it a factor. So let's try to understand this. So the claim is that this lambda gamma is a factor if and only if gamma has infinite conjugacy classes. So this means, which is abbreviated to ICC. So in other words, this means that that if we take a set of the form H, G, H inverse, O, H and gamma, then this set is infinite for every non-trivial element. Okay. Again, so let's try to check this. So let's do the following. So suppose we have an element in our von Neumann algebra of a group. So we take apply this element. This is our particular cyclic vector, this is our average vector, delta E, and decompose it in the orthonormal basis in our L2 space. Decompose this. This is well-convergent series in the L2 sets. And sort of one should think then that X is an element of this form. But this should be understood kind of in the right way. It's like with Fourier series. So this is like Fourier series of this element. It does not literally converge to a given element. So we have to understood it in the right way. Okay, and we'll try to understand. But it remembers everything about the element X, because remember our vector is separated. So it's zero only if X itself is zero. Therefore, in principle, these elements contain complete information about X, and we want to understand when such an element is central. So let's try to do it. So when is it central? So by definition, this means that it commutes with any other element. So we can say that this is the same as to say that we have this. if you want to check this, it's enough to take a scalar product with any other element. So we can say that this is the same as to say that this is the same as to yx for every y. Again, we don't have to take all possible y's, it's enough to take a dense a subset which spans a dense subspace. So this is the same as to say that O lambda G star hx lambda H is O lambda G star x. But now we use that this is a trace. This is the same as to say that this is O lambda H inverse G H star x. Well, and what these coefficients are, these elements xj, so notice that xj, by definition, this is x delta E delta G, so in other words, x delta E lambda G delta E, so in other words, lambda G star x. Right. So as a result, this is exactly the same as to say that these Fourier coefficients are the same for G of H. So the conclusion is that if you have this element is central, if you look at this Fourier series decomposition of it, then all these Fourier coefficients are constant on conjugacy classes. But at the same time, we know, of course, that sum of squares of absolute values of these coefficients, this is the normal of the vector x applied to the cyclic vector, so it's supposed to be finite. So therefore, if you have this condition, this already means that all these coefficients are zero on conjugacy classes. So therefore, if you have ICC, then this implies that all these xj's are equal to 0 for every g, not different from E. So this implies that actually x delta E is x E delta E. This implies that x is actually scalar. So therefore, an infinite conjugacy classes implies that this is a factor, and conversely, if you no ICC means that you can explicitly construct a central element. So if you find some conjugacy classes with some element set like this is finite, then you can just construct an element in the center. So then sum over H in C lambda H is an element of this. So therefore, it's indeed if and only if. So therefore, the conclusion is that as soon as you have an infinite group with non-trivial group with infinite conjugacy classes, and we get a 2-1 factor. This is a large supply of 2-1 factors. So let me just give you some examples of such groups. Examples. Yeah. Let's say we take the x plus b rational numbers. Or in other words, this is a group of matrices of the form Pt1, where A is rational and non-zero, and B is rational. So you can check, and maybe because this is an exercise, that this is ICC. Another example, canonical example, is the group of for finite permutations of n. So these are permutations of natural numbers, but with finite support. So we have only finitely many points which are permuted, and the rest of the points are not permuted. So again, this is another exercise. This is again ICC. And let's consider one more example. You can take the group with free group with n generators, and with if n is at least 2, then it will be ICC free group. N generators. ICC for n at least 2. Okay. Yeah. So let me give maybe briefly one more example of a large source of 2 factors, and then maybe we should make a
Sorry, the notation for A is what?
For what?
For A?
For A?
Yeah.
I mean, it's not. I just wrote something. It's X plus B group over Q. This is just a name for it. These are transformations. Which, you can think of it
that's
as
just the matrix version.
yeah, it's just
I
a
understand Q equals. Okay.
Right? So yeah, maybe we briefly consider one more source of 2 factors, and then we make a small break. Okay, so there is these are short class of examples, and we're not going to really talk much about it. It's just to indicate there is a huge source of 2 factors. In addition, just to coming from groups with this additional properties. So assume that gamma is a discrete group, and assume that gamma acts by measure preserving transformation on some probability measure space. It's, probability measure preserving. Action. And in this case, one can construct about cross product of L infinity functions by the action of this group gamma. And let me first formulate it a bit imprecise, and then I'll make it precise. So this is a von Neumann algebra. This is generated by a copy of L infinity function on this space, and elements UG for H to G in gamma, such that so these elements UG satisfy this representation of a group, meaning that UG, UH, this UG, UGH, let's say the identity is element UEE, And so the main rule is how these elements interact with functions. And the rule is the following. Well, when you want to compute an element UG function, you replace a function by the translation of this function by element G. So this is your. This does not completely describe the von Neumann algebra, but it actually will describe if I also specify the trace. So we define a trace, and the trace is defined in a very similar way to how we define here. Recall that here the trace on the group algebra, it takes a combination of this element lambda g and it picks up the element at identity. Here the typical element, that set of elements, will be a finite combination of this form, where f of g is a function and ug is an element here. And what we do exactly the same. We pick up the coefficient at the identity. But this is still a function, not a number. And then we integrate. This is our trace. So these rules are already completely specify the von Neumann algebra. But maybe I will just skip how we represent it concretely on a Hilbert space. So the claim is, which we are not going to prove, but in a way it's very similar to what we did here. So we look at this kind of Fourier decompositions, look what it means to be central. So you can do this kind of analysis in this case, but now dealing with the situation when these are not just numbers but functions. This analysis is very, very similar. So the claim is the following. So we'll then assume the action is essentially free. So this means that it's almost free or free in measure theoretic sense. Meaning that if you consider all points fixed by a given element, then the measure of this set is 0 for every non-trivial element. And the second condition is that it's ergodic, meaning that there are no non-trivial sets which are left invariant by the action. So in other words, so if AGA is a set which is almost invariant, so invariant modular sets of measure 0, and then either this is a 0 measure set or it's actually the full space. So in this case, again, the claim is that this gamma is a 2-1 factor apart from trivial cases when it's finite dimensional. If gamma is infinite, the infinity space is infinite. Or finite dimensional. The general case. And this produces you a huge class of, it's a huge source of 2-1 factors. Yeah, so I think let's maybe make a 3-minute break. Yeah. I mean, you can start with, if measure is not preserved, you can assume only that the measure is quasi-invariant. So it's in the same measure class, but it's not literally invariant. Right? So when you translate by a group element of the group, the measure, you get a measure which is equivalent to your given one, but not equal. In this case, you can basically anything. Then typically you get type 3.
Even starting with an action.
even starting with just one transformation. If you, yeah, that was also for examples. Also, you don't have to assume that this is probability measure space. You can consider the infinite measure spaces, and then you easily get like to infinity. Yeah. I mean, it's the construction itself is a more general construction, right? But this criterion is not a generalization of that one, because we assume this essential freeness, which in that case is certainly not the case. So this is not an if and only if condition. So for general groups, it's a bit not quite obvious when you exactly get a factor. So once you assume that you have essential freeness, then you get a factor if and only if the action is ergodic. But this condition is not really needed. It's only a sufficient condition. Yeah, if we start with a trivial case where our measure space is just a point with mass 1 at that point, then this construction will give us exactly the group phenomenon. Okay. Okay, so yeah, we'll consider this construction of coming from groups as our main source of examples of Pt1 factors for the purpose of these lectures, and one can ask, so how much? So I can say how much does this group phenomenon algebra of L gamma remember about gamma. And this is an area of very active research, and there is no, you cannot expect any uniform answer. It turns out that depending on the classes of groups, the answer can be very different. So there are very classes of groups, sort of rigid groups, for which phenomenon algebra even can remember completely the group. But there are some other classes for which it does not remember anything, basically beyond its cardinality. And so let's talk about the second class, which is much better understood and was understood much earlier. So let's give the following definition. So, discrete group gamma is called amenable. If there is a left translation invariant, state M on L infinity functions on gamma. So we require a state on bounded functions on gamma, which is invariant under the left translation by the group elements. And it turns out in phenomenon algebra there is a closely related notion called injectivity. So a phenomenon algebra inside V of H is called injective. If there is a condition of expectation, we'll see in a second, please. Condition of expectation E from entire algebra B of H onto M. So what conditional expectation means? This means that E is a UCP map such that E of x is equal to x for every x in M. So it's a UCP projection onto M itself, and moreover, then it turns out that it has an bimodular maps, in the sense that EXY is equal to EXEY, and EYX is EYX for every x in M and for every y in V of H. Yeah, from the definition, it's not obvious that these two notions are related, but it turns out that they're indeed very closely related. So the claim is that L of gamma is amenable if and only if L of gamma is injective. So yeah, let me sketch. Okay, yeah, so that's right here. Proof. Yeah, one of the things which let's start with going from amenability to injectivity. One thing which I forgot to say, which we could use by analyzing. So remember that our L gamma is sitting inside P of L2 gamma. And we have this ratio vector delta E, which defines our trace, and out of this we have this order conjugation. Remember, this is Jx delta E is x star delta E. So in this case, it's very easy to compute what it actually does. Right, all these operators, what they do. So let's do this computation. So recall that the regular representation is defined in such a way that delta H is operator corresponding to H of y to delta E. Right. So therefore, this is J lambda G H inverse delta E. Then we use this condition. So this is lambda H G inverse delta E, or in other words, delta H G inverse. So we see that this operator exactly transforms the operator of left regular representation into the operator of right regular representations, which are given by multiplication on the right. So therefore, lambda G, J is rho G, where rho G H is delta H G inverse. Right? So therefore, the commutant of the left regular representation is exactly the operator given by the right regular representation. So now, what we want to show, we want to show that amenability implies injectivity. So somehow we want to construct and condition expectation from all operators onto L gamma. So L gamma is operators which compute with representation, right regular representation. So somehow we have to start with any operator and produce an operator which computes with operators of the right regular representation. And the trick, which actually Mike used yesterday in the compact case, but you can use the same in the amenable case, is that as soon as you have something which is not invariant, but you can average and get things invariant. So therefore, the definition then is as follows. So we conjugate an operator by rho of G. So we want operator which is invariant under this operation. It is not, but then we can sort of average. Well, this literally does not make sense, but this is the idea how you define such a thing. And in the, say, compact case or finite case would be exactly the formula which Mike used yesterday to unitarize representation. But you can make a sort of precise sense of this. So more precisely, you can do this at the level of vectors. So in other words, what we have to specify is what this operator does to vector psi when taking the scalar product with some vector zeta. And what you do, okay, so you look at this function rho gx rho g star psi zeta. Now this is a nice function, nice bounded function. So g goes to this. This is a nice bounded function. Now we can apply the invariant. So this is exactly the same formula as this one, but this is rigorous but less intuitive. This is intuitive but less rigorous. But then you can check that this actually works. So this gives you V is a condition of expectation from V of H into the commutant of right regular representation, which is exactly operators of the vector.
It's normal.
No, this is not normal. Yeah, this is the very important remark. This is a very seldom normal. So typically not normal. Yeah, actually, if you have a conditional expectation from V of H on Neumann algebra, if it is normal, then M should be of type 1. So yeah, this is an important remark that this E is not true. Well, and for the converser, assume, and conversely, we have a conditional expectation from V of H and A of gamma. And somehow out of this, we have to construct an invariant mean, and the trick here is the following. So remember that we also have L infinity of gamma sitting inside our L2 of gamma. This is Robin discussed, so we have the operators of multiplication by functions on the L2 space. We can think of this sitting here. So what we do, we so we want to define a mean. So we start with a function on L infinity of gamma, and we think of this L infinity sitting inside algebra of operators, and we'll construct an invariant mean. So natural idea is that we apply this conditional expectation. But this conditional expectation doesn't give us a number; it just gives us L infinity of gamma. But L infinity of gamma, we have our nice trace. Remember that the trace is given by and it turns out that this is an invariant mean, and the key point is this is an invariant mean because we have the following relations, which were exactly from this example 3, that if we take lambda g, f lambda g star, then we get f g inverse. And check that at the level of operators we have these relations. When you apply then conditional expectation and apply the trace, you see that this exactly gives you. So therefore, these two conditions I need very closely related. Okay. So let's see some examples. Let's see. let's start with kind of simplest possible and the infinite examples. So let's consider just integers. The claim that this is amenable. So how to construct an invariant beam? We want to construct a function of L infinity function z, which is invariant under translations. And the observation is that, well, here we have L1 functions, at least, which are almost invariant under translations. Namely, let us consider the following functions. Well, in two, so we can see the characteristic function is that points from 1 to L. Right? So this is an element of L2 space of null 1. And this, if we use a translation, then this set as n grows becomes almost invariant under translation, or more precisely, let's say that this u psi n if goes to 0 and n goes to infinity, where u is our operator lambda 1, so the translation by 1. Right? They almost coincide, they don't coincide only at the first and the last point. Okay, but this means that if you consider corresponding states, they, as n grows, become more and more invariant. So what you can then say is that they m any cluster point in the Weak-Star topology of this state phi n of f so since these states become almost invariant, and any cluster point will be a state which is literally. Okay. This gives you one example, but starting from this example, you can actually. Yeah.
I guess before you mentioned so there was a comment about the non-normality of E, or actually if it was normal than n is like, could you maybe say a few words why some of these?
I mean, well, you have to, basically by definition, you have to analyze it. Yeah. I mean, it's not a kind of completely straightforward argument, so I'm not sure I can reduce it, but it's not a very difficult thing that I mean. Yeah, it's more than that. Yeah. Okay, yeah, but it turns out that out of just these examples, you can construct quite many. So by just using definition, we're not going to do it, but believe me that one can show that amenable groups are closed undertaken subgroups. Extensions. So if you have a group such that it has an amenable subgroup and the quotient is an amenable subgroup, then the group itself is amenable, and its products and direct limits, or if you want, I mean, just increasing unions of increasing sequences. Well, doesn't matter really, but yeah. Yeah, I mean finite products, okay, just to be on the safe side, let's say finite products. Yeah. Okay, if the question is what you mean by products, then it also goes under limits. So. Let's be satisfied with just finite products, and then it's certainly true. So out of this, you can construct quite many things. So for example, these two groups which we considered, the first ones, so this x plus b over q, and S infinity with finite supports. These are amenable groups. And if you trust this result, then the question is why? So can you see that this actually implies this? But the third group which we considered, which is the free group, is actually not amenable. So, for example, F2 is not amenable. So let's see. That's a nice elementary argument. So our free group is generated by has two generators. So let's call these generators G1 and G2. And we want to see that there is no invariant mean. For this, we'll construct the whole paradoxical decomposition. So let's consider the following four sets. So define the set A plus. These are all reduced words in G1, G2. So in F2, so meaning that you allow G1 inverse, G2 inverse as well, starting with G1. Let's consider A minus, same thing, but we start with G1 inverse. And let's do the same with G2. So we take a B plus, same thing, starting with G2. And we take D minus, same thing, starting with G2 inverse. So we divided all reduced words, which form elements of our free group. And these four sets, depending on whether the first letter is G1 inverse, G2, or G2 inverse. So then what can we say about these sets? So if we take the union of all the sets, so all the sets do not intersect, right? And the union of these sets, the joint union of all the sets, is the entire group minus the identity element. This is the only point which is not in any of these sets. But you can also decompose it in a different way. You can also write that the entire space F2 is also the union of A plus with G1 A minus, and also the union of B plus with G2 B minus. Right? Thank you. About it. To agree. So basically, if I have a verb, which is if it starts with G1, I'm already here. Right? If it does not start with G1, I can multiply it by G1 inverse, and there will be in A minus, and then our initial word will be here. Right. So therefore, we have this decomposition, and therefore, if we have now assumed that we have an invariant mean, assume that F2, this is an invariant mean. So one simple observation that as soon as you're dealing with infinite group and you have invariant mean, then the value of invariant mean on any delta function is 0. For the reason is that, just say that m of delta function is 0, simply because so since x1, xn in f2 are different elements, right? Then if I take the sum of these delta functions, this is still a function which takes at most value 1 at every point, so it's not larger than 1. Right? And if I apply our invariant mean, the value of invariant mean on any of these functions is the same, right? By invariance. So I conclude that m delta e is not larger than 1. And so the conclusion is we get this one, right? So therefore, that we didn't get the entire group there. It does not matter that much because we have m of delta e is not larger than 1. So we can ignore this, and then we apply our invariant mean, and what we get. So we get that on the one hand we have 1, the characteristic function of the entire group, minus this function, which does not matter, and this is equal to the sum of values of characteristic functions, values of the invariant mean on the characteristic functions on all these sets. But on the other hand, I can also have these two decomposition, and so I get that this is also this one. And I often use this decomposition, and see that it's also equal to this one. Right? And so this is obviously nonsense. This one, and their sum is still contradiction. Okay? So therefore, what we can learn from all this that so we have that amenability is a property which is remembered by the von Neumann algebra. It corresponds exactly to inductivity, and we have examples of ICC groups in conjugacy classes groups which are amenable, like those examples, and also examples where we have non-amenable. So in particular, the conclusion is that the group von Neumann algebra of F2 is not isomorphic to the group von Neumann algebra of X plus B group over Q, or group von Neumann algebra of permutations of finite support on N. Yeah. Okay. But what about the remaining one? Oh, well, I mean, the isomorphism of this group. So they are not isomorphic to our third group, but we talk about these two. Yeah, before we answer a question, let me also evaluate several other properties of injectivity, and we'll prove one of them because we'll need the argument later anyway. So one fact which we're going just to accept lemma is that if we have a von Neumann algebra inside B of H, then M is injective if and only if its commutant is injective. So the indication of the idea of the proof, you can see that, remember that in good situations we have relations like this, right? It's not always true, you cannot, like, for any m find that j satisfying this property. Just a second, but if you have this property, then everything would be fine, because you don't see really much difference between n and n prime. Yeah?
So what's the same need for algebras to be isomorphic, given that
Just as,
cases,
just as sister algebras.
as
But then they will, automatically imply more. So in particular, like these ultra strong, ultra weak operator topologies will correspond to each other. But this happens automatically.
or you don't want this to extend to something between.
No, we don't. So we kind of think of still von Neumann algebras as sort of abstract algebras. So we don't concentrate on just one particular Hilbert space. And if we do want a Hilbert space, we would rather find a very nice one where things like this happen.
Also, just as unital star algebras.
Or just unital star algebras, as I say, yeah.
But injectivity is a property that is defined in terms of A.
No, this is maybe another thing that this is one thing, but another one, injectivity does not depend on things. But this is actually an easier property. It turns out that for Neumann algebras, they have very simple representation theory. So basically, from any one H, you can construct any other H by very simple procedure. Taking infinite direct sums and cutting by some projections. Okay, so this one will just let's accept. But another one will improve, because I said we'll need an idea of the proof anyway. So assume that we have this decreasing sequence of von Neumann algebras. And assume that all of them are injective. And so let us consider the intersection of all these von Neumann algebras. And then the claim is that M is outside. So in some sense, sort of injectivity passes to limits. So let's try to prove this. So we have our conditional expectations from d of h onto Mn. And so somehow out of these conditional expectations, we want to construct a conditional expectation onto the intersection. And so we have to pass to some limit, but the limit does not usually normally exist literally, so we have to do something a bit better. So what we will do is the following: we fix a free outer filter. Free outer filter. So So what does it mean? So for me, the definition is simply the following. So we consider L infinity functions on N. So this is a commutative sister algebra. So it must be an algebra of continuous functions on some compact space. And this compact space is denoted beta n and called stone-check compactification of the n. And then inside this space, n sits densely. And what I will fix is just any point in this huge space. This is a really huge non-separable space. And I'll fix any point inside this space which is dotted. So what it allows me to do is that this means that any bounded function becomes a continuous function here. So it has a value at any given point. Or in other words, we can say that we have a value of a function when n index n goes to this particular point. So it makes sense to talk about makes sense to talk about limits. So if I have an element of L infinity of n, then if I view it as a function on beta of n, we have a value of f on omega. It's a continuous function, so it makes sense to write things like this. And if this sequence converges in the usual sense, it will converge to the same number. But, otherwise, it converges to something, and for me, it doesn't matter what it really means. It means only that we can operate with these quantities as with usual limits. But now they're defined for arbitrary bounded sequences. Okay. Okay, if I have this, then the idea of the definition is as follows. So we apply this conditional expectation here of x. Literally does not converge, but now we have this generalized limit. And the definition is that this is convergent in the weak operator topology when the limit goes to n to omega. Yeah?
So is this the same as saying that you can take Christie point in point sigma with topology of this?
Yeah. So again, this is maybe kind of the idea, but literally we again mean that just if I take ex psi zeta, this is what in the end I have to define. So I do the same here. We have en x psi zeta. Now this is a well-defined sequence of bounded elements. So this is a sequence to which I can take this sort of generalized limit. And you can check that it's all fine, and it defines your conditional expectation. The important thing, I mean, in this formula, we sort of implicitly use that the unit ball is a compact in the weak operator topology, but in this formula, you can say we don't even use that. So this is just the definition. Okay? So the corollary of this, you can pass to commutants. And when you take the union of two von Neumann objects generated by von Neumann algebras, then the commutant corresponds to the intersection of commutants. So therefore, by passing to commutants, you can also conclude it.
Here, finally, it does not depend upon that.
Sorry? No, it depends. But I don't care. We just need the existence. Yeah, it will certainly depend, but we do, unless there is literally. When it does not depend, this means that these things really converge. So the corollary is, again, that if we have an increasing sequence of injective, then if we take the union and close it in the weak operator topology, then this is also injective.
Silly question. Wouldn't you just use the same argument?
No. Maybe it's a good exercise to discuss for this tutorial, that why the same argument is not going to work here. Oh, it's not like this. So this is a good exercise. So we literally, not trying to repeat this, we just apply to pass to commutants. So the commutant of the union corresponds to intersection as a result of that. Okay, yeah, so there's 1 minute left. And this is almost enough. We'll give one more example and formulate the result. So one of the consequences of this is that now the corollary of the corollary is our hyperfinite to one factor is actually injected. I mean, this is one way of zero, but there are different ways. But and the reason is that it exactly is defined as an increasing union of just finite-dimensional von Neumann algebras, which are both injective. And here we then come to big result, fundamental result of Kohn. Says the following: that if H is separable, M inside B of H is an injective to one factor, then actually M is isomorphic to the hyperfinite factor. So it's a fantastic result which not only important in itself, but also the ideas which were used in the proof of this result, they still play a huge role in the development of operator algebra. So in particular since we already know for any non-trivial countable amenable ICC group, we have that with the group von Neumann algebra is isomorphic to the hyperfinite to one factor. So in the amenable case, the von Neumann algebra does not remember anything apart from this amenability. So in particular, we know that our two examples, which you considered, the group von Neumann algebra of X plus B group over Q is isomorphic to group von Neumann algebra of finite permutations of M. This is isomorphic to the hyperfinite to one factor. Correct?
I don't want to go up here. You want us to convention? No, use this time.
Yeah, that's
fine.
Okay, that's it for today. Okay, you got questions? Sorry? Yeah, I mean the word injectivity comes from injectivity of an object in suitable category. So you think of category of sister algebras with Marxism as completely positive maps, then this is more or less injectivity, but not quite still, because this is not an abelian category, so it's kind of still similarity, but not really from
Okay, if you don't have questions, then you resume at 1:15.